us answer this question. How many different computational problems are there? Consider these questions. So the first question is this. Say write a C program to print say 0, 1. Question number 2, write a C program to print say 0, 2. Question number 3, print say 0, 3. So like this, it's a closed interval and you are asked to write a C program which will list all elements in this. Okay. Whether such a program exists or not, can we really list, that is separate. We are only looking at how many questions of this type one can ask. We separately proved that 0, 1 is uncountable, therefore one cannot list, no algorithm exists, no C program exists. That is a different question. We are only asking like this, how many different questions are possible. So now one can ask print the closed interval ij, and ij belongs to R. You ask for all possible ij. Where do ij come from? Ij come from R. So now you see that how many different questions are possible. Number of questions is precisely R cross R, because you say you look at all possible closed interval I, j. We know that R itself is uncountable, so R cross R is uncountable, which means number of computational problems is uncountable in nature. So you won't be able to list, that is the consequence, right? One may not be able to list all questions, all computational problems. It's a valid computational question, right? Write a C program to print 0, 2. Write a C program to print 10, 15. Write a C program to print I, j for all possible ij. Which means number of such questions is R cross R, which is uncountable in nature. So number of computational problems are uncountable in nature. So as a remark, please note that questions are valid. On the other side, can we really solve these questions? Solvability versus unsolvability, that's a separate track. And for example, can we come up with an algorithm? Can we design an algorithm to list 0, 1? Can we write a C program to print all of 0, 1? We know that 0, 1 is uncountable, which means what? There is no listing or no enumeration, which means no algorithm or no C program can list all of this, which means no algorithm exists or no C program exists. When you say no algorithm exists, which means you cannot solve this. This implies that printing 0, 1 is an unsolvable problem. Now you see, we started off with discrete maths, discrete structures, and subsequently we moved on to theory of infinite sets, and now we brought the true connection between theory of infinite sets and theoretical computer science, or computer science in particular. Now you see that this is really what we are interested in when we look at theoretical computer science study, that given a problem, is the problem solvable? Does there exist an algorithm? Can you come up with a program which will halt for all inputs? And you see that questions like this, it's a valid computational problem and it does not have a solution, which means this problem is unsolvable. And there are many such problems. In fact, you have uncountably many unsolvable problems. Here is a fundamental question which has no solution at all. Now, this theory has brought in many interesting connections. On one side, how many questions? On the other side, it has brought this solvability, unsolvability theory. With that, it talks about whether a question has a solution or not. And having a solution is like algorithm exists. If no algorithm exists for a question or a computational problem, you say problem is unsolvable. And here is an interesting case study which is unsolvable, and there are many. All of these are unsolvable, and there are many unsolvable problems in computer science. In fact, this theory, the one that we will be studying a little later, and all that will talk about computation and how to understand the notion computation. And in an attempt to understand the notion computation, we talk about solvability theory and unsolvability theory. And here is one case study, and which says the printing the closed interval 0, 1 is unsolvable. Fine.